Hello all, thanking you all for joining the next session of 5 minute software testing. Uh, we are continuing the unit 3, that is on static analysis and reviews and metrics, and this is the lecture 3 in that unit 3 series. So today we study about static analysis aspects. So before that we'll try to recap so what we had studied in the earlier static analysis session. So we continued about static analysis, control coupling and data coupling, data flow analysis. We know that the program path, the worst case path will be exercised in terms of the programming structure and all that in the control flow, and in terms of data coupling and data flow, we consider the use of the data, how it is going to be interfaced between two different functionalities or procedures, and referenced variables defined how it is being typecasted, global variable anomalies, whether same names are used in local, etc. All this will be analyzed statically with the help of the program. So basically static analysis will be done during the unit testing stage or during the integration testing, but the emphasis during unit testing is on project standards and code. As per that, it needs to be analyzed against, and such as no go tos, breaks in all cases, procedure size, all this will be analyzed to see that the correct program and the program is within the safety definition of the unit what is being implemented. Similarly, unused items such as unreachable code or unused variables will have to be removed. That also will be analyzed during the static analysis. Similarly, the architectural aspects of the program such as designs, low level or high level designs also will be inspected for the control flow and the data flow. So there we will see how the parameters are flown between different functions and how the function is going to flow. So control coupling and data coupling can be done during the integration. Mostly the integration could be software integration or the hardware software integration. So next one, we had gone through some of the static analysis tools such as understand for C++ or ADA from SkyTools, Polyspace, Coverity, QAC, Cantata, LDRA testbed. All this can be used for testing or static analysis. Basically, they provide the call tree, the usage of the variables, procedures, the complete report, line code, the Maccabee complexity, what we have studied, and of course the inbuilt tools such as MISRA tools will be part of the IDE, the integrated development environment itself. So we can run through the tool such that it generates the report that what are the info type errors or what are the warnings or the violations that we have in terms of MISRA rules. Similarly, we have Logiscope, rule checker, PC-lint, likewise. So also we had gone through a sample snapshot of understand for C++. Here you can see the invocation. So with the help of invocation of different functions, we can understand the control flow. Similarly, the variables, unused objects, and all that will be analyzed with the help of this tool. The other tool is check marks. So one sample report also we have seen in terms of how deep the control flow can go from left to the rightmost. You can see the various procedures or the functionalities have been called. So typically this is the call tree that will be produced during the static analysis. As part of the static analysis, we also do the WCT and BCT. BCT stands for best case execution time, and WCT stands for worst case execution time. So basically it provides what is the worst possible execution time and the worst possible execution path that system can take during its execution. So that will be analyzed against the stringent or the performance or the real time requirements of the implemented embedded system program. So that also will help in terms of how much we can optimize, which functionality we can optimize in terms of comparing various units such as algorithms, any closed loop control systems. All this will be measured. It's a very important aspect of this static analysis that WCT, control flow and data flow have to be measured. So additionally, for timing requirements, memory requirements and all that, we use logic analyzers, oscilloscope and any support tools such as emulators, time accurate simulators, etc. Also there is another aspect of static analysis that can be done is with the help of a test hook or the test code that will be inserted into the software, and there are software profiling tools which will help in terms of analyzing the call stack, stack memory, stack analysis or stack overflow we will study today. All this will be done with the help of the inserted code. So that is also a part of static analysis. Here we can see an example of static analysis, the relationship between WSET, VSET and possible program execution time over the right hand side which runs the time, and we will define the possible execution time in the center and the tighter execution times and the safe execution times likewise. So there is a bounty analysis they call it. So all the top ones will be done as a pre-analysis, and for the post analysis the static analysis will be done on the functions that are implied within the program in terms of flow graph, call graph and the WSET bounds it will produce. So coming to today's session, stack analysis and stack overflow and stack overflow ISA guidelines. We will study about this. Okay, so what is stack analysis? We know what is a stack, which is a memory part of the program which will be used dynamically during the execution of the program. When there is a preemption or when there is an entry exit of different functions of the procedures, the stack will be used for the purpose of saving the state and retrieving the state. Stack is a memory part of the embedded program which will have store or save and retrieve. That will be keep on doing over the execution of the embedded program such that there is no loss of data during preemption. Preemptiveness, basically this will help in preemptiveness of sub functions from the main functions or the subroutines from the main routines, main to sub, and in order to reserve some of the variables during this execution, this will be used main to sub and reserve the space for storing the state or temporary variables, whatever it is, depending on the state where the main routine was used. So it needs to save the current state and the flow or the variables that it is using, and once the subroutines calls are done going back to the previous routine, all the saved one will be retrieved and the execution will continue. So similarly we have ISR, interrupt service routine. So what it does is whenever there is a ISR, or it's also called as a exception, so what will happen is the ISR takes the priority, and before ISR invoking, whatever the preemption happened on the routine or the procedures, it will say the state of that routine in terms of the states, the variables, or the program counter where it was. Then once the ISR is returned, that state will be retrieved back and the execution will continue. So for this there is a dedicated that is called stack. So this stack has to be defined during linker. We know that compilation and the linking is two aspects. As a result of linking, we know that object files are produced along with the map of the complete embedded system program. So what we do, there is a linker file which defines the all the memory basically, but in particular the stack which we are of interest now. So this stack basically will be defined in terms of how much the program is going to use. This is basically based on the complexity and the level of nesting, the subroutine calls, the number of ISRs, all these matters. So based on that, the stack will be defined. It could have 1K, 2K, whatever it is, depending on the complexity of the program. So the stack will be defined, and at any point of time, the stack needs to be within the certain range. That means so what will happen is, so suppose let's assume that this is a stack, and the total size is say this is a lower bound, this is the upper bound, and we have say 1 kilobytes. So what will happen is this area will be utilized by the program, and the stack will usually grow from the lower to higher side usually. So whenever there is these events like subprograms, subroutines, or subfunctions are executed, or there is a preemption from the ISR, the stack memory will be used in order to save the states and the variables inside the stack, and it will start saving from lower to higher likewise till the last phase. So we have to make sure that while doing the linking, we will allocate a sufficient stack such that at any point of time it will not overflow. That means the stack cannot go beyond the allocated memory. So that is what we have to ensure. How this will be done? There are different tools and techniques that are used, but this will be part of the static analysis. So that is what the crux of stack analysis. So basically we need to see the stack program, how much it is allocated, and the stack usage will be calculated based on the embedded application, how much size it's going to take. Okay. So stack analysis. Stack memory has to be allocated statically, and by the programmer, as I said, during the compile time this will be allocated. Underestimating stack usage can lead to serious runtime errors because we don't know the behavior of the program, because it is not able to save because already the stack memory is overflown and it is not predictable. So definitely we need to have a buffer of the stack at any point of time during the program execution. So it's difficult to find the stack issues. Overestimating stack usage means a waste of memory. You know that too much memory we have and we use a very less space of stack is also of no use. So typically in embedded industry they suggest designer to have at least 50 to 75% of usage, so that there is a 25% of stack as a buffer. So that is that standard they imply. This is about 25% of memory. Sorry, even memory also they recommend like that. Stack usage should be reserved, is what they specify. Okay. So we should not have a overestimate as well as we should not go overrunning the stack. That's what is very important. And the stack analysis calculates the stack usage of embedded application. The analysis results are valid for all inputs and each task execution. Definitely, each task we should be knowing how much it is going to use the stack. So the results will validate all this. So basically, stack analysis calculates the stack usage of the embedded application. Stack analysis can directly analyze on binary executable. Yes, we know, because binary executable is the one which will be running throughout the embedded software execution, exactly as they are executed in the final system. Stack analysis not only reduces development effort but also helps to prevent runtime errors due to stack overflow. Definitely, stack overflow is one of the typical common errors that we have seen, especially in the application field such as VC, VC++, VB, whatever it is. But in embedded applications where we are not clear about where our program is going to go, or where it is not clear for the designer to design how much to reserve, and he would have defined a limited memory, definitely there is a chance that the overflow occurs. This is why? Because programmer knows about the program what he has developed, but there are different things along with the program what he has developed, such as libraries he could have used, which he is not aware of how much it is going to use, and there are certain assembly code he doesn't know how much it is going to occupy the stack, and there are certain support functions or subroutines, or here I used some third party hooks or code which he is not aware. So those are the areas where we see there is a stack overflow. I mean, the chances of stack overflow is there. So that needs to be meticulously analyzed. That is what stack analysis is about. Preliminarily, the analysis can be done on the map files generated during the build process. That means once we build, after the linking, we generate a along with the binary executable the map file. The map file will clearly tell how much executables, where is the start, where is the end, and all that. So based on that, we can analyze the stack. So that is about the stack analysis. Next one. So there is a stack overflow problem. So what is that mean? Stack overflow. So we will study that. Depending on the programming language used and the implementation of the compiler, various problems may arise in the event of stack overflow. The problems manifest themselves as, that means what are the problems that we are going to come across when there is a stack overflow. So what are those? A corruption of data. If the stack overflow causes the software to write into a data location, definitely we are going to have a unintentional write into a data location, so that can cause the corruption of the data. Machine exception, because there is a stack overflow adjacent to protect memory and we are trying to write either or access the code which are read only memory sort of a thing. Definitely there is a unwanted exception for this. Then an unpredictable program execution, that means the execution cannot be controlled. If the corruption of data occurs and the code addresses are corrupted, definitely the code can behave wayward. We don't know. the return addresses of a function can be corrupted and return may be improper, etc. So definitely it's unpredictable. And the fourth type of issue will be a software exception. We have seen machine exception, where the processor itself generates the exception for a internal exception which is predefined. In this case, the software exception, if the program contains code to check the stack, if that is there, then we have a software exception. So basically, the purpose of stack overflow is to guide for determining whether software design should implement protection mechanisms to cope with the stack overflow. Basically, it tells what is being designed, whether stack flow is going to happen or not. So this is very important typically in industry where they follow standards such as D1 So there is a D1 guidance regarding the stack usage and stack overflows in the areas of code reviews and requirement based verification. However, it does not cover the possibility that a data corruption may occur and lead to stack overflow. So that's very important dynamically when we execute to have this considered in terms of data corruption. So the purpose of stack analysis for the stack overflow is to provide details of specific aspects of stack usage and stack overflows, so which should be attended appropriately. Okay, and so sometimes in different programs they will have a secondary stack as a additional buffer. So a secondary stacks are used less frequently, they are used less, and their use is typically under the control of runtime functions. Stack checks are often put in place to monitor the all secondary stack usage. That means there will be a piece of program already in the embedded software which can be monitored as well. With the help of that, the data that it reports we can monitor and arrive at whether the stack is fine, if there is no overflow, like this. So it's something like a runtime check on the primary tasks, primary stacks, so and as well as the secondary stacks. So this can be done with the help of review of the source code and the map file, and overflows should be addressed by requirement based testing as well as integration testing. Basically, it is done during the integration testing. It could be software integration on the target, actual target. This will be performed. That stack analysis and stack overflow will be performed on the actual target. So analysis of the theoretical worst case scenario helps to determine whether the use and implementation of stack has been well designed in order to adequately manage data that needs to be handled through stack usage. That means we know that the worst case scenario, how much it is going to take, what is the amount of time and memory it is going to occupy. So that also will help in terms of analysis of the stack. So stack analysis of worst case stack use consists of identifying all the functions in the program and obtaining their stack frame size. So we need to know all the and their stack size. We need to collect it, and stack size means stack frame size, and also we need to determine the call graph, who is calling who, which function, what is the call tree analysis. So based on the determination of the call graph for each separate execution thread, that means the different path, independent paths, that is nothing but a task. So stack analysis will be done, and we need to combine all the data during this worst case stack size execution. So this will be definitely done in the source code level. So basically by counting the size of all data requisitions and parameters. So we don't need to do manually. There are tools that will report the size. So the size needs to be analyzed manually. Okay. The next one is on Stack Overflow. Another set of information. An unintended stack overflow may occur during the execution of a program for various reasons. Now we have seen the issue that is going to cause after the stack overflow, what it can yield, whereas whatever the reasons that we are going to have for stack overflow is as per the below. So they are a hardware failure, a software development failure, software development error, that means it's not designed properly. A hardware failure could be a memory is word out, or memory is corrupted, or there is a issue in any of the parts that is not behaving appropriately. Okay, so and the other one could be an unintended software behavior. There are software bugs which is intentionally not written, and memory corruption. We know that memory corruption could be hardware as well as software. So another term is called single event upset. So due to some program issue or something, there is a one event that is caused everything in terms of spiraling different issues that could lead to a stack overflow. That's what it means. So this needs to be done by testing sometimes. That means you need to analyze the behavior. So typically they take the approach by filling the memory with certain memory pattern and to execute a test which force the maximum usage of the stack. So what will happen is so here is the stack and it is filled with a known pattern such as A in the first line and F is filled in the next line. Likewise, it is filled. So we know that the stack is filled here. Then we do some testing. Make sure that the testing makes the program write the value of the stack into this area. That means it is being overwritten by the stack data. Suppose this much is written or this much is written. We know that the program that we have tested has utilized this much stack. It means this much is still reserved. So we read this portion. We know that definite pattern is there, and we are able to read it. We know that that portion of the stack is not overwritten by the stack data. So we know that there is still space available in the stack, and the stack has not overflown, or we know that how much stack is used. So based on that, analysis can be done. So simple programs, it will be easier, whereas if there is a complex programs, definitely we need to have a thorough stack analysis, especially in level A software. Level A is the most critical software they use in the aerospace embedded software. So in such cases, when a stack overflow occurs during the execution of this level A software, the consequences could be catastrophic, as the software may be out of control. We cannot predict. Definitely we cannot afford to have aerospace when it's flying having trouble of all this stack. Definitely that needs to be analyzed appropriately. Although an SEU, that is a single event upset, is unlikely to be repeated, it's single time is going to happen. If a stack corruption or an overflow occurs due to a software error, then given the same program state and input conditions, the software will be repeated. Such a repetition may cause the recovery mechanism to be ineffective. So it is very difficult to recover such errors, which is spilled out of single event upset and followed by the overflow or the software error. Okay. So coming to the next slide for the stack analysis, we have ESA guideline. The ESA, European aerospace industry, so which have a stringent guidelines about quantifying or qualifying the embedded software for aerospace. So their guidelines, as per their guidelines, the following 4 points have to be considered for stack analysis. What are they? An analysis should be performed to define whether or not it is necessary to perform continuous stack monitoring based on criteria such as the software criticality, stack type, the use of built-in monitors, etc. See, what will happen is typical embedded software in the airlines industry or aerospace programs will have a monitoring functions. That monitoring functions also will have a stack monitoring functions, and if there are stack errors, if it finds, there will be a definite recovery from the stack analysis in terms of a reset or reporting, whatever it could be, if it is reaching beyond a certain limit, likewise. So that should be analyzed. So that is what it means. The next one, if continuous monitoring of the stack is used, it should be performed in real time. That means if the monitoring part is there within the embedded software, the critical embedded software piece, then it should be performed during the real time. That's what it means. The monitoring mechanism, example, the monitoring of the stack pointer should be specified in the requirements. That means this monitoring function also will be a requirement, because without requirement we are not able to have any program running on the target on field or will be delivered. Definitely, as per the requirements, the monitoring function will be developed, and this monitoring function will monitor the stack continuously. So this needs to be analyzed during runtime, and that needs to be reported. In the event that the monitor detects an overflow, the expected behavior means an exception or the interrupt should be specified and verified accordingly. That means if there is an issue with the stack, such as overflow, the same thing needs to be mitigated within the program with the expected behavior with raising of the exception. So that is what we can do, so that we know what is the issue for that particular exception. It is because of stack overflow. So to conduct a runtime monitoring of stack overflow, it is not a difficult one. Basically, it is an implementable one. It is an additional piece of software, but it is still worth, because the criticality is very important. So based on that, requirements also will be laid out. And the monitoring policies also, different strategies are followed basically based on the type of stacks. I mean, what sort of stacks they are having, and it's a data stack or a program stack, executive level or counters, etc. So based on that, analysis need to be taken care. So that is what the stack analysis of embedded program will be carried out, especially in the aerospace industry. That is what the guidelines talks about. Okay, so with that, the stack overflow we are done. So next we will move on to the coding standards. analysis. We are done with the stack analysis. Now we are moving to the next aspect of static analysis, that is the coding standards. So this is a very important static analysis that needs to be done. Though you think that coding standards is only for the coder or the programmer, which is not true. Static analysis has to be done on the implemented code or the program that embedded software has, with the help of an independent reviewer, whether the standards and the guidelines of the coding have been properly adopted during the programming phase or the coding phase of the embedded software. It's very much important, we need to understand. So what are the things that we are going to have in coding standards? Okay, so coding standard defines a set of rules for programmers to follow in a given language. So there are levels of guidelines they give, like it could be a guideline, it could be a rule. So in such cases where we have rules that has to be mandatorily followed, I'll just try to write out. Guidelines will be there, and we have rules, which is very much mandatory. Guidelines are something like not mandatory but recommended or optional, something like that. Okay, so that needs to be followed during the programming. So programmer could have missed it, or he would have ignored, or there is a flaw while programming due to a last minute work or during a rework, something would have missed. It doesn't matter if it's a comment or if it is a warning, whatever it is, as part of the programming, all this need to be stringently followed in terms of coding standards. And the program may be working on the field very fine, but definitely it has to have a proper way of maintaining the code in terms of coding standards. That's very important. Okay, the next one is a C coding standard can help keep bugs out of embedded software by leveraging common language features and development tools. Definitely, there are number of tools that the programmer should try to use, whether that program is having any issue in terms of coding rules, whether there is violation is there. Basically, because we may not see the hidden issues of the embedded software, which are laid out purely in the coding standards. By following the coding standards, definitely it will keep away the bugs. There are language features which needs to be taken care. Of course, sample coding standard rules we can try to go through, but it's not the scope of this software testing. But all we need to know is what is the coding standards, how it is being used, and how it will be verified. That is what we are trying to understand, and its importance. That is also one of the thing. Okay. So basically, coding standards, if it is followed properly, it increases the readability and portability of the software. That means the software is in a good shape to understand somebody. Your readability is not somebody can read it easily. It is understanding. That means the program is quickly analyzed. The program can be quickly analyzed and understandable way. If it is implemented, it is easy to use it or reuse it, or whatever you want to port it to a different platform, that embedded software, or you can scale it, or it can be maintained by different people, or it can be tested easily, analyzed easily. So that is what the basic purpose, along with the hidden bugs that could be there when implementing. So it reduces the time required by individual team members to understand or review the work of peers. That we know that we are going to have a different types of reviews, and the reviews will be done independently. That means if 4 people are there in a program who are working as a implementer, that 4 people will be shuffled for doing the reviews of the implemented program. That means person A will review person B's code, person B will review person A's code. So likewise, it is easier if and it is going to take less time if the coding standards are followed appropriately, because the reviewers are quite aware of the programming standards or the coding standards. So the typical embedded industry coding standards they use MISRA C 2004, which has about 100 plus rules, 108 or something. So that rules are categorized as guidelines and regulatory. Regulatory is how need to be followed, and guidelines are something like optional. And specifically in automotive industry, they use this MISRA C. Okay. So basically, potential benefit of a coding standard, people will ignore. Sometimes they will do a prototyping, rapid prototyping, agile, whatever it is. But basically, they need to have this process in place, because the later part of the program, especially the complex programs, will be difficult if the standards have not been followed in the earlier stage. It is not going to cost much if the standards are proper and properly used by the programmer. The following that is not a expensive one. Definitely is going to save, basically because it is going to prevent a bug from creeping into the code. So thus a key strategy for keeping the cost of firmware development down is to write code in which the compiler, linker or the static analysis tool can keep bugs out automatically. In other words, before the code is allowed to execute, better we follow the coding standards. Of course, there are different sources of bugs in software programs. But that is all the next level. Basically, these bugs could have been injected or introduced or created by the original programmer, but it could come out as a hidden issue or the bug in the later stages of the program when the program is running for some time, like months or years. Till then, it is not revealed. So it is difficult to fix if it is found after a few months. The program was developed today and the bug was found after a few months. Difficult to fix such issues because readability or the coding standard has not been followed. We don't know where the issue is. Typically, the number and severity of bugs introduced by the original programmer can be reduced through disciplined conformance and certain coding practices, especially something like placement of constants on the left side of each equivalence test. That means we know equal to and double equal to, there is a difference. The programmer would have put one as a logic and the other one as assignment, so you would have missed, so that could lead into a issue, and coding standards following that will definitely ease out such issues. The other aspect of coding standard is the commenting. We know in C we use this comments, or we use this in ADA. Yes, ADA assembly. So it's very important to have a disciplined use of consistent commenting and stylistic practices. That means we need to have a consistent comments, like the comment should be so and so, it should be very brief and descriptive, and it should be within the 80 lines. All this have to be practiced properly. So everybody in the organization can easily understand the meaning and the proper use of the functions, or procedures, variables, etc. So there should be a meaningful name as well as the comments above. Usually above they put it in the C program. It depends on what standards you want to follow. It could be below or side of the program, anywhere, but it should be consistent and easier. Okay, so that is about coding standards in this slide. So we will go through some of the coding standards rules, what the code should look like basically. Here you can see uh, coding standard set of rules, what the code should look like uh, indentation rules. They call it as example, use start stop layout. Vision start stop is a famous C++ and C programmer. Basically he has written a book and he has put a indentation rule. Basically we can follow that, and code we can have typical specifying a subset of a language. That is better don't use new or throw, especially in C++. Predictability problems will be there. Typically specifying rules for commenting, how we should be commenting. Every function must have a comment explaining what it does. We know that there should be a proper description and comment for that function. Also the lines that are within the function, the programmatic lines, often requiring the use of certain libraries. That means IOStream, stdio, printf, all this will use it. So to avoid safety issues, uh, we have to use it appropriately. So we need to follow the rules. Organizations often try to manage complexity through coding standards. That means the complexity we are going to dilute it in doing appropriate coding standards, so that any of the complex program can be easily controlled. Often they fail and create more complexity than they manage. That is what they say. So this is what the sorts of programming rules talk about. Continuing on the coding standards, a good coding standard is better than no standards. We know that. So this is also again a statement from Storstrup. He is one of the pioneer in C++ and coding standards. It could be a multi-million project or a multi-person, multi-year, whatever it is. So without coding standards, definitely they are not going to start it. He says that way, but even for a smaller project or any 1 month, 2 month project, or it could be hundreds of lines, we need to have a standards and a process that is followed. A poor coding standard can be worse than no standards. So that is also another thing that he is trying to tell. C++ coding standards that restrict programming to something like the C subset do harm. They are not uncommon. So that is all typical issues. So C++ coding standards could restrict the C usage because both are inclined together. All coding standards are disliked by programmers. These are some of the facts that he is telling. So good standards also people, the programmer don't like to follow sometimes, but the independent IB&V team make sure that they are all in place. All the programmers want to write their code exactly their own way. That is the problem. A good coding standard is prescriptive as well as restrictive. Means it should be very crisp. Here is a good way of doing things as well as never do this. That means you should tell both assertiveness as well as negativeness in terms of standards. Standards should specify both things, restrictions or limitation or restrictions of what should not be done, what should not do, and prescription also it should be telling what is a good thing to follow. A good coding standard gives rationales for its rules. That means there should be a rational or reason for every coding standards and rules with an example. So that will make easier to maintain and review. So that is what starts up programming recommendations, and the aims or the goals of the common coding standards are as per below: the reliability, the portability, maintainability, testability, reusability, extensibility, readability. So these are the important aims or the goals of the coding standards. I'll repeat: reliability, portability, maintainability, testability, reusability, extensibility, readability. So these are very important aims for developing the coding standards and following the coding standards. Okay, so few sample rules we'll try to go through for coding standards, which are obviously obvious to follow for any typical embedded software implementation. Okay, so what are those sample rules? No function shall have more than 200 lines. You know why? Why? Because it's very difficult to maintain such program. If there is a bug while doing the fixing, the chances are that there could be a bug in another place. So it is a creation of a new bug while fixing the existing bug. So better to have a program having not more than 200 lines. So ideally they say 30-50 lines or not more than 100 they say, but definitely not 200 or more. Here what he says is 200 non-comment source lines, not that complete program. You can have a description in 2-3 lines. So for 40-50 lines you may end up in 200 total lines. But what he talks is about the EOC. I think I told in one of the session about EOC, executable lines of code, executable object code. I'll again repeat. So some statement is there, or by semicolon is one executable statement. Even just semicolon is also a executable. Similarly, for we have this floor bracket, and with the floor bracket constitutes one executable. Similarly, while so and so, if else if is one executable, and what are the contents of this if else if is also a, it will act as a another executable statement. So likewise, we cannot have 200 executable lines in the any function or 200 or more. Each new statement starts on a new line. We cannot have something like semicolon followed by another statement like this, which is a violation. We cannot have multiple statements in single line. That is one of the strict rule that has to be followed mandatorily. No macro shall be used except for source control. That means we cannot afford to have macros in the program unless we have a source control. That means we have a if def and if sort of a thing. Identifiers should be given descriptive names. That means the name should be very much sounding like what it is going to do, what is the intention of that particular variables. Identifiers here means it could be a local variable, global variable, or any object. So we are going to identify with the identifier. So that should be small narrative or descriptive in terms of that particular signal. It could be something like motor speed. So this is a variable name. So we cannot afford to have MS. People will write or M, they will write, or S will write. So it is not a good practice because even for the programmer himself it may be difficult to maintain and execute. So hence it is better to have a meaningful name for the identifiers. So it can contain common abbreviations and acronyms. When used conventionally, X, Y, I, J, etc. are descriptives, but better to use number of elements style rather than the number of elements like this. So avoid all these single letter things. Instead of that, if you want to mention number of elements, better to use number of elements this way. So that's what his suggestion is. Toss-up. You can have either way, but it should be meaningful and understandable. So what he is trying to say here is O should be capital, E should be capital, and N also can be capital, such that it is highlighted properly and readability. So type names and constants start with a capital letter. That means the name of the constant or a type name always should start with a capital letter. Here you can see device driver starts with capital D, buffer pool starts with the B. Similarly, identifiers shall not differ only by case. So we cannot have head and head once caps and small. It's very difficult to maintain. Better head followed by something small head, or it can lead or it can lag, whatever it is. So better to avoid this kind of a anomaly. That's what it says. So all this have to be. What I have put here is coding standards has to be in place, and that should be analyzed. It's part of the static analysis by the independent tester. That's what it means. And by doing this coding standard static analysis, the common objectives such as reliability, portability, maintainability, testability, reusability, extensibility, and readability, these are achieved. So that is what the coding standards importance. Some more rules we go through. Identifiers in an inner scope should not be identical to identifiers in an outer scope. For example, we cannot define an inner scope variable with the same name like where here you can see where is defined outside and inside also same name. So we don't know what is going to be used. We know what is going to be used, but the user or the maintainability perspective, it is not easier to maintain it. So better to have a specific name, meaningful name. Declarations shall be declared in the smallest possible scope. Variables shall be initialized. It should be initialized. Definitely, any variable we cannot just declare like this. It should be declared. Should be used something like int var equal to 0, or depending on what initialization value is needed, it should be used. Next one, casts should be used only when essential. So unless otherwise is needed, we should not be using the cast typecasts basically. Code should not depend on precedence rules below the level of arithmetic expression. So we should not have a dependency on the precedence. So we should always try to see the implied behavior of the program. Based on that, we need to have precedence rules defined. Here, for example, x equals a star b plus c. Here, multiplication is the precedence, followed by plus. Then b plus c will happen first, and a will be multiplied. That is not the way. So this is okay. So here in this case, you see it is ambiguous and precedence is violated. You can see parenthesis if a less than b or c less than or equal to d, definitely it is going to violate. So rather than that, you better do a parenthesis for this as well as this. So that will avoid the ambiguity as well as Some of the compilers, what will happen is the precedence would not have been defaultly defined, so it may take a different way. So to safeguard against those issues, it is definitely better to have precedence taken care in the program. So that needs to be analyzed appropriately. These typical issues that I have seen in the embedded industry, precedence rules have to be followed appropriately. Especially this is useful in arithmetic expressions as well as logical expressions. Increment and decrement operations shall not be used as sub expressions. That means we cannot have int x equal to v and within the array as an index that is being used as a sub expression. So that increment might be overlooked. So we don't know what is the predictable behavior of this. So better to avoid this, and outside you do the pre-increment. So that is what the coding standards sample rules is about. Okay, so we will continue the coding standard rules, coding rules power in the next session, and also we will study about the reviews, inspection, and process in the next class. So today we studied about stack analysis, workflow, coding standards, and objectives of the coding standards. So that is the end of the session for today.